right, so in section 2 of unit 6, conservation of energy is what we're going to be talking about today. When we talk about conservation of energy, we are talking about a closed system. Okay, that means what goes in is what goes out. In other words, mechanical energy initial equals mechanical energy final. Okay, so what that means is this: our total kinetic energy that we have in the beginning plus our potential energy in the beginning has to be the same as the kinetic energy plus the potential energy that we end up with. All right, that really is everything. Now, conservation of energy, if it is not a closed system, breaks down into the following. For an open system, in other words, we've got something closed system means everything's happening inside this circle. We've got kinetic energy, we've got potential energy, they may be changing. Now, for an open system that we have, when we're talking about that, this changes. Mechanical energy in initial still equals mechanical energy final, okay? But what's different here is that we have initial kinetic energy, initial potential energy is going to be equal to our final plus our final, but we have to take into consideration that we may be losing some energy somewhere along the way through dissipative energy, okay? That may be friction, usually, in our case, all right? So what we've got, it says two answers. One involves a closed system, other involves an open system. We've already kind of talked about this a little bit. So in a closed system, the energy, the total energy, remains constant. Remember, we're talking about this circle and nothing's going in, nothing's going out. My energy is my energy. We're staying in this circle. Now, for an open system, what you have to consider is that that circle now has energy, but it also either has stuff coming in or energy going out, okay? So we have energy in and energy out. So the system gains or loses energy from its surroundings. And guys, sometimes this is based on how we define the system. If I define the system, if I have something going on, like say, I want to jump off a cliff. If I want to jump off a cliff, a closed system would be me plus the earth. An open system would just be me, because the earth is going to be giving me, in that open system, the earth is going to be giving me that energy, that gravitational potential. But because I didn't include it in the system, I just included me, it's acting and feeding energy to me into that system. Hopefully that makes sense. So let's talk about what a closed system is. Closed system, no exchange of conserved quantities, and that would be either mass, energy, charge, with its surroundings. And in an open system, there is an exchange. With the surroundings. Now, if we were talking about an energy bar chart sort of deal, then with your closed system, your bars would still all add up, and so would it in your open system. But the big thing is that in that open system, you would have that dissipative energy there, okay? Now, let's look at this guy right here. It says, consider a human body. To what part of the human body is the height measured when calculating gravitational potential energy? Explain this in terms of a pole vaulter. All right, we measure the height from our, oops, didn't mean to include right R with spell it so badly, from our center. I know you won't know what I'm going to say now. Center of mass. Okay? From our center of mass. Reason why is because you've got to get, as a pole vaulter, you've got to get your center of mass up over the bar. If you can get your center of mass up over the bar, you can get the rest of you up over the bar. All right? And that's really what's happening when they're flinging themselves the way they're flinging themselves. Okay? So if we look at this and we're measuring the height from our center of gravity, which means that if I were to do an energy bar chart here would be all U sub G, and it would be all just U sub G at that point. Now, if I'm measuring it from in the middle here, I'm measuring my height somewhere from here. Okay? So now, if I look at my energy bar chart, I now have U gravitational and kinetic energy at this point. And quite frankly, I have spring potential energy because look at what's happening. My bar is bending in this section right here, isn't it? Okay? So my bar is bending here. I'm kind of going backwards, actually. To tell you the truth, I should probably start here, where the only thing I have is I'm running. So if we did this guy, we would know we started with just kinetic, and it would be the same height as what I ended up with. Now, in the middle, and notice that these are the same, okay? Same number of bars. If I were to do this the right way, and I would say maybe it's 4 bars here. And so this would also be 4 bars. However, in the middle here, where I've got flexing going on of the pole, I'm still moving through the air, I'm in motion, and I'm getting further up off the ground, then what you're going to find is maybe I've got 2 bars here and 1 bar of each of these. But it still has to add up to 4 total bars. Okay? Now, what's the equation for the force that a spring exerts on an object? Well, we know spring force is equal to Kx. That's my equation. This is my spring constant. Units, of course, are in newtons per meter. You know that. And X is going to be the spring stretch. Spring stretch from equilibrium point. All right. Now let's check and make sure we understand what's going on. We haven't done the hot water lab yet, but we will be doing the hot water lab. Okay, so just hang out here on this one. We'll come back to this guy in a minute. All right. Although I guess we could actually technically answer this without having done it yet, because it said when you did the hot water lab, the system consisted of the water and the heating coil, is not a closed system. Why? If we've got water here and we're checking the temperature with a thermometer, right? Okay. And we have a heating coil. Why is it not a closed system? What do we find out what's happening here? It is open. Is all the heat from the heating coil going straight into the water? The answer to that is no. Some heat into the room, okay? Not only that, but the energy for that running that heating coil comes from the outlet, right? So how do we make it closed? We would have to include what? Our original system. We'd have to include the cup, the water, the coil, the room, the air in the room, the power grid. You can see how this gets crazy. The power grid, the power plant. When do we stop? See what I'm saying? So sometimes we just have to settle for an open system because closed system would just be way too hard. All right, so now, roof of Rock Hill High School is about 20 meters off the ground. That is a hint right there. That tells me that we have got some gravitational potential energy, right? So that's going to be a U sub G of some sort. If you jumped off the roof of Rock Hill High School, how fast would you be going upon reaching the ground? How fast tells us that we probably got kinetic energy, correct? So what we want to do is and it says, think about what types of energy, write it and solve. Does your mass affect the answer? So we know that mechanical energy initial has to equal mechanical energy final. We're going to assume we're in a closed system, okay? So initially we have, let's just write it out. Kinetic energy initial, U initial equals K final plus U final. So now, in the beginning, we are starting from rest 20 meters off the ground. That means I have no initial kinetic energy. Now I'm going to end up on the ground at the end, which means I have no gravitational potential energy, which means this is mg h equals 1/2 mv final squared. And this would be h initial. So what do we notice here? What you should notice is that the doggone mass doesn't matter a bit, does it? It sure didn't. So we're going to come over here and we're going to notice that GH initial is going to equal 1/2 V final squared. We want to know how fast we're going, so we're going to multiply both sides by 2. So times 2 times 2. So we end up with V final, once we take the square root of 2G initial height. Well, if we plug that in, we get a V final of square root of 2 times 10 times the height, which was 20 meters. So we end up with 20 meters per second is our answer. All right, now suppose you're 50 kilograms and you jump off the roof 20 meters high. Time you wear a crude parachute caused you to reach the ground going 10 meters per second. How much energy was taken away by air resistance? So we know mechanical energy initial equals mechanical energy final, which means we started, let's just do this the whole way. We know we're losing energy somewhere, so we have energy dissipative here. We know that this originally was 0. This is final is 0. So what we're left with is this equation here. mgh initial equals 1/2 what? mv final squared plus dissipative energy. All right, so now we just solve. Our dissipative energy is going to be equal to that original mgh initial minus the 1/2 mv final squared. M does matter this time. So we know we're 50 times 10 times 20 minus 1/2 that 50 times, we ended up going 10. And we end up with about 7,500, and that's joules because it is energy. So we're just subtracting. So it all hinges, if you haven't figured that out yet, it all hinges on this equation right here. Okay? Now, student in gym class wants to measure the speed he can dash straight. Okay? So now we're going to look at this. And forward, student is a friend who wants to help, but friend only has a meter stick, no stopwatch. Okay? There is a rope for climbing suspended from the ceiling. Explain how the student can use the meter stick, the rope, and the conservation of energy equation to calculate his dash speed. All right. So we are going to, we've got a rope hanging. What can we do here? All right, we want to calculate our speed. Well, I'm going to think about the fact that I know that if I start with kinetic energy initial, can I convert that to gravitational potential final? Ooh, I sure can, because we already know that if we don't have any dissipation, if we think that it is an actual honest to goodness closed system and its conservation is there, then those should be equal and opposite when we're done, or equal when we're done, right? So if we stay, we're going to start with kinetic energy initial, and we're going to end up with gravitational potential energy final. Then this 1/2 mv squared initial has to end up equal mgh final. Well, the m goes away, so what matters is the final height. And that final height can lead me to what this initial velocity is. So my plan is to run at this rope. I'm going to run at it, grab it, and let myself swing upward. So I'm going to let myself swing upward until I reach some particular height, and I'm going to measure the difference in my height from the ground to how far I rise. Okay? So I'm going to run at the rope, grab it, and swing up. I need to measure far above the floor I go. So my independent variable will be what? My height, I rise, and dependent is going to be my velocity. Is it or isn't it? Be careful, guys, because in this case, really what we're measuring is we are starting at different speeds. So my velocity is, and my dependent is the height I go to. We're going to measure our dependent to get our independent variable, though. Isn't that fun? So this is going to be our guy that we measured. Okay? So our force is actually going. So now, let's look at a couple examples here. Example 1. 4 athletes participate in a competition. Each has a mass shown in the table and runs towards a long vertical rope with an initial speed shown. Okay? Each athlete grabs the end of the rope and their motion causes them to swing upward, stopping at a max height h from the floor. The competition's organizers realized they forgot how they were going to determine a winner, rank the athletes from winner to loser based on the following, and explain your reasoning. The height they each reach. Okay, so each person is going to start with, we're going to do mechanical energy initial equals mechanical energy final, aren't we? They're each going to start with kinetic energy, and they're going to end up with gravitational. So we have 1/2 mv squared equals mgh. The m of the mass of the athlete doesn't matter. Okay, what does matter is the one with the greatest height is going to be 1/2 v squared over g. So the speed is going to determine the height. So as our speed goes up, h goes up. So who has the greatest speed? Well, that would be C and D, so those have to be equal. And those are greater than the other two, which are the same speed, so A and B. Now, the potential energy here, again, we have 1/2 mv squared equals what? mgh. But what does each one start with? Well, each one starts with a different mass, so we have to figure out what their mass is. So let's look at this. So for A, we're going to see 1/2 mv squared, and that's not going to change, is it? So it's still going to be 1/2 mv squared. For B, you'll see my method of my madness here in a minute. 1/2 2m v squared. So now I'm just at mv squared, so it has more potential, it has more kinetic, because as the kinetic energy goes up, the gravitational potential energy goes up, doesn't it? So let's see. So C has 1/2 m, but now we have 2v squared. So we end up with 2mv squared. And then D finally, 1/2 has 2m and 2v. So we end up with what, 4mv squared? So D has the highest, followed by C, followed by B, followed by A. Okay? Assuming the length of the rope is at least as long as the height attained, does the length of the rope affect any of the rankings? The answer is no. L, which is the length, never appears in any of the energy equations. Okay? Next example, we've got a ramp, 2L by L. Now, how it's oriented in a mass, M and 2M. Between case A and B, they're the same ramp with two different masses. In case C, the ramp is turned the other way with mass just M. Speed of the block, reaching the bottom. So let's figure out what's going on. So we're going to call this H, and this is theta in each of these cases, because that's still the same no matter what. Okay? All right. So how do we figure out the speed of the block? Well, let's figure out what we got. In each case, we start with gravitational potential, which in this case will be mgy equaling 1/2 mv squared. So what do we know? And this is for each block, so they'll have the m or 2m. It'll still cancel out, won't it? All right, so now we end up with gy equals 1/2 v squared. So if we solve this, we get v is equal to the square root of 2gy. So what do we know? We know as y increases, the velocity increases. So which one has the highest y? That would be the third one, case C. So case C is bigger, and then A and B have the same gravitational potential energy, so those are the same speed as they hit the bottom. Kinetic energy. Well, kinetic energy is a little bit different. The kinetic energy is going to be equal to mgy. So again, as y goes up and m goes up, k increases. So which one has the biggest y and the biggest combination? So we have to check because we don't know. For A, we have m and L. For B, we have 2m and L. And for C, we have m, 2L, and G. So for me, it seems like these two are the same. So we know that B and C are equal, but they are greater than A. Ranking tasks. I love ranking tasks. Net force acting on the block as it slides down the ramp. Well, the net force is going to be the acceleration times the what? Here's a fun way to think of this though, guys. Energy or work, maybe we got to think about this backwards. Work is equal to force times distance. Well, work is a type of energy, okay? So what we're going to do instead is say our force, we're going to manipulate this as our work divided by the distance it goes. In every single case, this would be our work divided by h, because the distance down the ramp is the same for all of them. So really what we need to think about is this work as what kind of energy are we starting with? All right, in every case, it's going to be gravitational potential. Our force is actually going to end up being mg for A. We know it's going to be equal to mgl over h. For B, it's going to be equal to 2mgl over h, so it's bigger. And for C, it's going to be equal to mg times 2l over h. Okay, so again, B and C are the same. And those are both greater than A. Which, if you think about it, makes sense. It's a shallower and it's lighter, so it's not going to go down. It's not going to need as much force acting on it. Acceleration of the block. Well, we know the higher the force, acceleration increases. Does it though? What do we know? F equals ma, right? So it's dependent on, the acceleration is dependent on the force divided by the mass. So really what we're looking at is our acceleration is equal to that force divided by the mass. So it really depends on what's happening here. We know B has A and B, well, B has the highest mass, but it also has, or A had, I should say this correctly. Let's just work this out. What do we know? Force acting on the block. Well, guys, by now you ought to know that that is mg sine theta, right? That's the gravitational force acting on the block. So that mg sine theta, so let's look at it this way. Mg sine theta equals ma. Oh, and what did we remember? The higher the angle, as theta increases, acceleration increases. So we weren't even looking at that at all, at force and mass, because it's too confusing. We're going to look at the angle, and you know that. As the angle increases, the acceleration increases. So clearly, the angle in C is the highest, so it's going to be the biggest, and the angle in A and B are the same, so they're going to be the same. Oh, that's a good review. That one is a good, nice little add-on from the last unit. Did I miss? Yeah, I thought I did. I thought I missed a page. Test our understanding here. All right. Block of mass M is connected to a spring of constant K. Block starts with a speed V initial, height Y initial above the floor. So we know it's starting with kinetic energy. It has initial kinetic energy. But first, we always want to write mechanical energy initial equals mechanical energy final, because we're assuming this thing is going to be a closed system, right? All right, and it experiences frictional force, so it can still be closed, it can still be conserved. Okay, so it's going to start with kinetic energy initial because it said speed. It has a height, so we know it has initial gravitational potential energy. Now, and the spring starts with a stretch, so it has spring, initial spring energy. Now, we know it ends with a speed V final, so it has final kinetic energy. It has gravitational potential energy final, and the spring has a stretch. But it also had frictional force, so we have to say that there was some sort of dissipative energy there that makes up the difference. So let's plug all this in. This is 1/2 mv initial squared. This is mg, h initial, height is y initial, plus 1/2 kx initial squared, because that's spring potential energy. It's going to end up with this much kinetic, that much potential, that much spring, and this is due to friction. So it is force of friction times the distance that it was going, and it said some distance. What was the distance? Oh, a distance x. So I need to be careful and make sure that I write this as x, because that's the distance it experienced friction over. And that would be our equation. Now we have a 2.5 kilogram block sliding on a flat, smooth track with an initial speed. Okay, so we know it has kinetic energy to begin with. Slides up a rough, long incline, so we know there's friction. Vertical height of 2 meters, so we know it's going to gain some potential energy and gravitational potential, and has a final speed, so it also has kinetic energy to end with. All right, so what we're going to talk about is we're going to figure out, it says calculate the number of joules of the energy each block has initially. So initially it's just starting with it's moving. All right, so this is going to be kinetic energy initial, 1/2 mv initial squared. So that's 1/2 the 2.5 times the 8 squared. We end up with 80 joules of energy. What does it have finally? Well, we know it has final kinetic energy, so that would be 1/2 mv final squared. So 1/2 2.5 4 squared. That is going to be equal to 20 joules, so it lost quite a bit. U gravitational final is going to be mgh, so that's going to be 2.5 times 10 times it rose a vertical height of 2, so that is 50 joules. So I can already tell you what it's lost from friction, and that would be work due to friction, which is, of course, what's left. And what's left, this is 70 joules, so that would be 10 joules left here. Okay? Now it says draw a bar chart for the block system. Okay, so it started with 80. Okay? Some of it went to gravitational, right? And some of it went to dissipative. Okay? All right, so now we know that it had 20 left here, so there's my 20. I knew it ended up with 50 here. And it ended, no spring, and it ended up with 10 here. So now I can draw my bar graph based on what I knew. All right, now it says, what's the magnitude of frictional force that acts on it? Well, I know that frictional force times the distance is equal to that dissipative energy, which is work due to friction. Well, we know that is force due to friction times the distance it went. How far did it go? It went 5 meters, and it was equal to 10 joules. So the force of friction would be that 10 divided by 5 would be 2 newtons. Okay? All right, so let's look at this guy. We have a block. Now we've got another more complex example here, but this is bringing it all together. We're doing different representations. We've got a block 10 kilograms compresses the spring force constant of 4,000 newtons per meter at a distance of 0.2 meters. Entire assembly is on a frictionless platform that's 0.45 meters high. The block is released from rest, so it's going to spring out, right? And reach its natural length just as the block reaches the edge of the table. Okay? So we got to think about what's going on here. What does this thing have? Well, this thing is above the floor, so it initially has gravitational, and it's pushed back on the spring, so it has spring potential. Okay? So let's figure out how much of each it has. So U gravitational is going to be equal to that mass, which is 10, times gravity, which is 10, times the height above the floor, which was 0.45. So this is going to be 45 joules, okay? We got 45 joules of energy here. Now, U spring, 1/2 K x squared, which is going to be 1/2 K, which is 4,000, times X, which was 0.2 squared. Okay, so that would be, gotta do a little calculating here. We end up with 80 joules. Okay. Okay, so let's draw this in. We know 80 if we go by, oh gosh, stop that. 10, 20, 30, 40, 50, 60, 70, 80. Okay, so I want to do 80 bars here, and we're going to do 45 here. All right, so far so good. Now what's happening here is we've got some, what's going on? We've got some spring that's going to be what? Going into the system or out of the system? It's going to be going, well, actually it's how we think about it. The spring is actually feeding energy, giving it to kinetic energy is really the way we should look at this for kinetic energy. So it's giving some of its energy to kinetic, right? Gravitational is not contributing because it has not gone off the edge of the table yet. So what do we know? We know at the edge of the table, and I'm going to do that one in blue, at the edge of the table, we need to know how fast this thing is going. We don't know. So let's actually look at this and say, okay, block speed at the edge of the table, we're starting with 1/2 kx squared, and we're going to end up with 1/2 mv squared, aren't we? Because we know we're starting with, and really I just did this the wrong way, mechanical energy initial, mechanical energy final for that part. We're starting with U spring, and we're ending up with kinetic. So the half can go away. We're going to end up with K, which is 4,000, times our 0.2 squared, equals our mass, which was 10, times our velocity, which we don't know. So if we solve this for a velocity, we end up with 4 meters per second, okay? So we end up with a 4 meters per second velocity, which means our kinetic energy here is 1/2 10 times 4 squared, which is 80 joules. Well, that kind of makes sense if you think about it, because this didn't change at all, did it? This is still above at 45. We now have no spring, so it all must have been converted to 10, 15, 20, 30, 40, 50, 60, 70, 80, sorry, here. So it really makes sense if you think about it. Same amount of energy. So now, what's happening? The kinetic energy is now what? once it leaves the edge of the table, whoop, leaving the edge of the table, now the gravitational potential energy is going to make it speed up even more, isn't it? It's going to transfer some of it into the kinetic energy as well. So now what do we know? Well, we know that all of that energy, which is 80 plus the 45 joules, is going to give me 125 joules. So we got 100. So it's actually going to go all the way up to here, if we think about it. All the way to there at 125 joules, and no spring, no gravitational potential energy. So now we can take all that 125 joules and set it equal to 1/2 mv squared if we want, v final squared. So multiply that, we get 250 equals 10 v final squared. So we get 25 equals v final squared. So v final is 5 meters per second. And those energy bar charts really help us, don't they? Now it wants us to calculate the horizontal distance. Well, I don't know what the horizontal distance is. I've got to figure out how long it's what? In the air. Oh, wait a minute, I do know, because I know the V initial right here, and that's all horizontal if you look at this picture. Boom. So V initial in the X direction is going to be 4 meters per second. So I know my distance, D or X final, is going to be V initial times the time. Okay, well, I still got to find the time. I know how far it is. I know what Y is. Y final is going to be equal to what? Y initial plus V initial in the Y direction T plus 1/2 AT squared. Well, Y final is 0, and V initial in the Y direction is 0. So we end up with negative Y initial equals negative 1/2 GT squared. So this thing started at 0.45 meters above the ground, negative 1/2 times 10 T squared. We end up with a T that is actually 0.35, approximately 0.35 seconds. So now we can take this back over here and find that our final distance, our range, is going to be that 4 times that 0.35, which ends up as 1.2. Well, hold on. It might not be 0.35. Let me double check this. Okay, 0.3. I don't know what it's thinking. 0.35. So this is 0.3. So 1.2 meters is our final length. Now, if the block strikes the floor and does not bounce, what do we know? But the floor is frictionless. How much energy is lost during the impact with the floor? Okay, well, we have K initial, which we found out was what? 125 joules, right? We have initial kinetic energy of 125 joules. How did I get to that? That's what we found out on our bar chart up here when it first hits the floor. After it lands, if we do 1/2 mv final squared, which would be 1/2 that 10 times 4 squared, we figure it was only 80 joules. All right, so 125 minus 80 is equal to 45 joules lost. And that would have been lost to sound, right? Banged on the floor, and we're good. All right. Block of mass M is compresses a spring of force K, constant K, a distance of X. Oh, here's our assembly again, right? So we know we have a mass M, spring constant K, it's compressed X. Tire assembly is on a frictionless, at a height H. Block is released from rest, that tells us initial velocity. Launches the block forward, forward, that tells us all of the velocity initially is in the forward direction. And it reaches the end table, travels a horizontal distance D as a projectile. Describe how each change listed below would change the distance. Okay, so what do we know? Increasing the spring constant. So if K goes up, we know the spring force goes up, right? Which means that U sub S goes up because it's 1/2 kx squared, right? So if we have more U sub S, then that U sub S is going to be transferred into kinetic energy. So block goes faster. At the edge of the table. So more distance D. It goes further. If it's going faster, it goes further. So now, if I increase the mass of the block, my gut is going to be less D. And let's see why. Okay. Since F equals MA, more M means less acceleration, doesn't it? Less acceleration means your final velocity is lower, right? As it leaves the table. So it doesn't go as far. Okay, increasing the spring's compression, X. Well, if you squish the spring in more, you're going to have more distance, aren't you? More D. For exactly the same reason as I. And what about the height? Higher table is going to increase gravitational potential energy, right? And it's going to take more time for the ball to hit the ground. So it travels further. So we're going to say more D. Now, the speed of the block upon reaching the end of the table. Okay. Well, initial mechanical energy equals final mechanical energy for this. We know it's starting with spring potential and it's ending with kinetic. So 1/2 kx squared equals 1/2 mv squared. The half goes away. We want to know the speed. So the speed is going to be the square root of kx squared over m. Time that the block spends as a projectile. We know the height is going to be equal to what? We know the initial position. We know the final position is 0. So we end up with the height equaling 1/2 gt squared. So the time is going to be 2h over g, square root of it, equals time. Distance d, the block travels horizontally. D is going to equal v that we found in the first one times the time. So we're just going to plug in v, which is the square root of kx squared over m, times the time, which is the square root of 2h over g, which means we just put all of it underneath the square root, 2kx squared h over mg. Now it says use those to explain. They are directly proportional. K K is directly proportional to V